Welcome everyone again to the next installment of this little series we're doing. Today we're going to go through the probability mass function. So if you remember from last time, we talked through what a random variable is, and in that discussion we used the example of an unbiased coin flip, which I'm just going to copy here, except I'm going to use x as the notation this time instead of the capital V. So just like last time, the value of the flip can be heads or tails, and let's denote heads as 0 and we'll call tails a 1, and each of these happens with a probability of a half. So we want to essentially transform this into a function which takes as input the possible outcomes of this random variable, so in this case heads or tails, and as output gives us the probabilities of those outcomes. So in this case, for both of them, it's a half. And just as an aside, before we really get into it, I want to talk about functions a little bit for those who may be unaware. So what exactly is a function? Well, we can think of it as simply a transformation that takes in an input and maps it to some output. So if I draw us a little box here, this is the function f. This will take in an input and it will spit out an output. Now it can actually be multiple inputs and multiple outputs, but for simplicity's sake we'll just take one. And so we'll denote the inputs as green, x, and the outputs can be blue, this bluey colour, y. And in fact, another way of writing this output is f of x. So the function takes as input the x and f of x is the output. So to really clarify that, let's draw this link here. So the x comes as the input as the argument, and the function itself comes as the function, I guess. Yeah. So let's try and take an example. So again, it can be any transformation. So let's keep it simple, and just say y is equal to let's say 2x. So it simply doubles whatever input you pass to it, which is a transformation. And with our notation, another way of writing this is f of x is equal to 2x, right? Okay. So that kind of covers functions. So going back to the original problem, we want a function that takes as input x the possible outcomes of the random variable and spits out the probabilities of as y, the probabilities of those outcomes. So coming back, let's write that down kind of mathematically. So we have our function, probability mass function outputs, fx of x, and we'll say that that equals the probability that our random variable x is equal to some specified value we give. Yeah. And I appreciate that I've thrown a curveball here with the subscript x here. And so to clarify that a bit, when we write these probability functions, we normally denote the subscript letter as the random variable, or it could even be random variables that we're trying to associate the function with. So just to try and clarify that a bit, the probability mass function as we've written it here is some function of the inputs x, which are the possible outcomes, associated with the random variable capital letter x. And that is a broad definition of what the probability mass function is. So let's try and kind of relate this back to our example. So we can draw a graph here. Let me go back to white. There you go. So let's draw ourselves a graph of this relationship. So as inputs, we have x, which are the possible outcomes. So as we've discussed, it can either be a 0 for heads, or let's say a 1 over here for tails. And the output is the probability of that observation, which in our case will be a half always. So let's kind of formalize this. We have a point here and a point here. There you go. And these are always, just to clarify, these are always, in both cases, a half. Boop, 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 because it's an unbiased coin. So this is a graphical representation of the probability mass function. Now this brings us on to another point, which is, well, can any function be a probability mass function? And the answer is no. And so the way to check whether a function is a probability mass function is to simply say, well, the sum of all possibilities, or the sum of the probabilities of all possibilities should be 1. So let's kind of take that as an aside, right? So how do we check if this probability mass function is valid? So is it valid? So we simply have to confirm that the sum of all the input possibilities of the mass function, that the sum of those are 1, which is another way of just saying that probabilities sum to 1, which is a core concept, right? So let's take our example again, where we say for the coin flip, we want to test this. So sum over all possibilities of the probabilities. We can say that is, in our case, the function at 0 and at 1. So plus the function at 1. And only those two scenarios, because all other points are 0 on this line, on this graph. So this is simply a half plus a half, which indeed is 1. So this is correct, and this is a valid probability mass function, which is great. So let's have this as another condition here. So the sum over all of the inputs of the function for the probabilities outputs should sum to 1. Okay, so this is another important concept, that probabilities sum to 1. So we've written in our example this relationship graphically. Let's try and write this mathematically. So again, we take the outputs here, the function, and this is equal to it will either be, again, half for heads or tails, or 0 otherwise. So for the inputs, it would be a half for the inputs being in the set. This symbol means sort of in, and when you do two squiggly lines, that denotes a set. So when x, or the input, is in the set 0 or 1, heads or tails, the probability of observing that input is a half. And otherwise, it's the probability of observing any other input is 0. So to denote all of the other inputs, we just say otherwise. Okay. And an even more concise way of writing this would be as follows. So we could even say this is equal to p1 minus p, and let's get our inputs of x and this term here. So the inputs are, or well, the variables here, x as the input, again, can be in the range or in the set 0 and 1. And in our case, p, which denotes the probability of one of the outcomes, will be a half. So p is a half. So I appreciate I rushed through that a little bit. So let me explain a bit more about this equation. So we know that the inputs here can either be 0 or 1, right? So let's first take the case when x is 0. Well, if x is 0, we get this p to the power of 0, which itself, anything to the power of 0 is 1, so that term becomes redundant, and we only have to concentrate on this residual term here. And 1 minus 0 is 1, so you end up with just 1 minus p. Now in our case, p is a half, so the output of this whole expression would just be a half. So when x is 0, when we put in heads, we get as output a half, which is right, which is what we want. Likewise, let's put in 1 or tails. When we put in a 1, now this term, 1 minus x, will turn into 1 minus 1, which is 0. And again, anything to the power of 0 is 1. So this term here becomes redundant, and we only have to concentrate on p to the x. Now p to the x then turns into p to the power of 1, which is p, which in our case is a half, which is correct again, right? So we want, when we input the possibility of a tails, we want the output to say the probability of a tails is a half, which is again correct. And this mass function is actually called the Bernoulli distribution. So it's used to model a discrete random variable, a discrete binary random variable. So that is a discrete random variable with two possible outputs. And this will always be valid for any value of p. X will always be always be either 0 or 1 because it's a binary discrete random variable. And this will be valid for any value of p because if we sum over all of the input x's, you simply get, again, the 1 minus p term plus p. So 1 minus p plus p is 1. And so we fulfill this term right here, making it a valid function, a valid probability mass function. So yeah, that's we've kind of run into our first formal distribution here, and I hope that this has sort of shed some light into what the probability mass function is. And yeah, I guess I'll see you next time when we'll probably start to look at the continuous case a bit closer, which gets a bit more complicated. So I'll see you then.